Functions typically also return values, and these are returned using return variables. And in the case of Solidity, the return variables are specified after the returns keyword. And Solidity functions can return single return variables, or they can return multiple variables. And these variables, return variables, can also be named return variables, where they have a specific name or names, or they can be unnamed. These are treated just like local variables within the context of the function. And in the case of unnamed return variables, an explicit return statement needs to be used to return that variable as a return value that goes to the context of the caller function. So we have the caller that calls the callee. The caller specifies arguments that get assigned to the respective parameters of the callee function. The callee function works with these parameters in the context of that function, does something with it along with all the local variables that might be defined within that function. It can also use the state variables that are declared within that contract, and once it is done with that logic, it can return values back to the caller. Modifiers. Function modifiers are something unique and specific to Solidity. They are declared using the modifier keyword, and the format is something like this. You have the modifier keyword followed by the name, and then you have a set of statements very similar to a function where you have some logic encapsulated within that modifier. And you also have an underscore. And the reason for that is how the modifier is used along with the function. So in this case, if there is a function foo on which this modifier is applied, then the control flow, whenever this function foo is called, goes first to the modifier. And depending on any of the checks, any of the logic implemented within that modifier, the function's logic gets called at the point where the underscore is used within that modifier. So if there are a bunch of checks in the modifier after which the underscore follows, then those checks really implement some preconditions that are evaluated before the function's logic is executed. But that underscore could also be specified before the checks in the modifier, in which case the function's logic gets executed first and then the modifier executes its checks. So examples for the usage here could be access control checks that are implemented as preconditions on the function in the modifier, and they could be post conditions that could be evaluated if the underscore happens to be before the checks in the modifier, and these could really implement some sort of accounting checks in the context of the contract. So these function modifiers really play a critical role because they're very often used to implement access control checks, things that allow a contract to specify only certain addresses, for example, to call the function where the modifier is applied. So this is something that is often used and becomes critical when you evaluate the security of smart contracts. Function visibility. Similar to the visibility that we talked about for state variables, functions also have a concept of visibility, and these can be public, external, internal, or private. So 4 different visibility specifiers. Public functions are part of the contract interface, and they can either be called internally within the contract or via messages. External functions are also part of the contract interface, which means they can be called from other contracts and via transactions, but they cannot be called internally. Internal functions, on the other hand, can only be accessed internally from within the current contract or contracts deriving from it. Private functions, on the other hand, can be accessed only from within the contract where they are defined and not even from the derived contracts. Similar to the state variable mutability that we talked about, functions in Solidity also have a concept of mutability. This affects what state can they read or modify. Depending on that, there are two function mutability specifiers, view or pure. View functions are allowed only to read the state but not modify it. This is enforced at the EVM level using the static call opcode that we discussed in the context of the EVM. And there are various actions that are considered as state modifying that are not allowed for view functions. These include writing to state variables, as should be obvious, but they also include emitting events, creating other contracts, using self-destruct, sending ether to other contracts, calling other functions not marked view or pure, using low-level calls, and using inline assembly that contain certain opcodes. Pure functions, on the other hand, are allowed to neither read contract state nor modify it. The not modification part can be enforced at the EVM level, like we discussed, but the not reading part cannot be enforced by the EVM because there are no specific opcodes that allow that. And there are again various actions that are considered as reading from the state. Reading from state variables is the obvious one, but also accessing the balance of contracts, accessing members of block, transaction, or message that we talked about in the context of EVM, calling other functions not marked pure, using inline assembly that contain certain opcodes are also considered as reading from the state of the contract. So the read-write mutability aspect of functions, again, has security implications, as you can imagine. Solidity supports the concept of function overloading. That's something fundamental to object-oriented programming. This means that it supports multiple functions within a contract to have the same name, but with different parameters, different parameter types. And this process is called overloading. Overloaded functions are selected by matching the function declarations within the current scope to the arguments supplied in the function call. So depending on the number and the type of arguments, the correct function, although it has the same name as other functions within this context, is correctly chosen. Note that return variables are not considered for the process of resolving overloading. So this notion of overloading is an interesting one that is supported by Solidity, given that it is an object-oriented programming language. Free functions are functions that are defined at the file level. So they are defined outside the scope of contracts. These are different from the contract functions that are defined within the scope of the contract. And the free functions always have implicit internal visibility, and their code is included in all the contracts that call them, similar to internal library functions. And these functions are not very commonly seen. Events are an important concept in Solidity that we encounter very frequently in smart contracts. They are really an abstraction that are built on top of the EVM's logging functionality that we touched upon in the Ethereum module. Emitting events cause the arguments that are supplied to them to be stored in what is known as the transactions log. This log is a special data structure in the blockchain. They're associated with the address of the specific contract that created them and incorporated into the blockchain. This log stays there as long as that block is accessible. The log and its event data is not accessible from within the contracts, not even from the contract that created them. This is an interesting fact of logs in EVM. They're really meant to be accessed off-chain. And this is allowed using RPCs. remote procedure calls. So applications off-chain, interfaces or monitoring tools can subscribe and listen to these events through the RPC interface of an Ethereum client. And from a security perspective, these events play a very significant role when it comes to auditing and logging for off-chain tools to really know what the state of a contract is and monitor the state along with all the transitions that happen because of the transactions. Up to 3 parameters of every event can be specified as being indexed by using the indexed keyword. This causes those parameters to be stored in a special data structure known as topics instead of the data part of the log. And putting parameters into the topics part by using the indexed keyword allows one to search and filter those topics in a very optimal manner. And like we just said, it can be used for up to 3 such parameters. Index parameters are commonly seen. They're also part of some of the specifications such as the ERC20 token standard and the events in that standard. These index parameters use a little more gas than the non-indexed one, but they allow for faster search and querying. Events are triggered by using the emit keyword. So every contract would declare a certain set of events as relevant, and within the contract functions, wherever these events need to be created and stored in the log, they would be done so by using the emit keyword. An example would look like this. Let's say that we have a deposit event as part of a particular contract, and we have specific parts or functions where we would want to create this event and store them in the log. Then this would be done by using the emit keyword as shown. So the syntax would be emit deposit, the name of the event, followed by the arguments that are required according to the parameters of the event. These look in some way very similar to a function call, where the event corresponds to the function and the arguments that are supplied to it correspond to the event parameters. And from a security perspective, it's critical for the contract, for the developers, to emit the correct event and also to use the correct parameters that are required by that event. Now, this is something that is sometimes missed or not paid attention to because it's perhaps harder to be tested and not really critical to the control flow of the contract as perceived by the developers. But like we mentioned, events are really the only way for off-chain entities, any kinds of user interfaces or monitoring tools, to keep track of the contract state and the transitions by looking at these event parameters stored in the logs. Now let's jump ahead and take a look at what structs are from a data structure perspective. We will revisit structs in the context of types when we dive into the various types within Solidity. But from a data structure perspective, structs are custom data structures that can group together several variables of the same or different types to create something very unique to the contract as required by the developer. Structs, the various members of the structs are accessed using the dot syntax. So if a particular struct, say S, has 2 members, let's say user and amount, then wherever we want to refer to the user component of the struct, we refer to it as s.user, and the amount is referred to by s.amount. So this is an aggregate type that is commonly used within Solidity to pack together custom data structures, and this is also something that you may be familiar with from other languages and often encountered when we look at Solidity smart contracts. Enums are another user-defined custom type in Solidity. They can be used to represent a finite set of constant integer values as represented by the members of the enum. Every enum needs to have a minimum of one member and can have a maximum of 256 members. Because they really represent the underlying integer values, they can be explicitly converted to and from integers. An example looks as shown here. Let's say that we have action choices as the enum. It's declared using the enum keyword, and the two members are go left and go right. One can declare variables of the specific enum type as shown. So here choice is a variable of action choices, and it can be assigned the members of action choices. So here we are assigning action choices.goRight to choice. And during the course of the contract function, different members can be assigned to that variable and it can be read from. Now this is really used to improve readability. So instead of using integer values, one can use specific names that correspond to those integer values in the context of what makes sense from that contract and its underlying logic. Now let's look at the concept of constructors in Solidity. This is a concept that is very specific and unique to Solidity because it really applies to smart contracts and the way they are created on Ethereum. Now if you recall, contracts in Ethereum can be created from outside the blockchain via transactions or from within the Solidity contracts themselves. When a contract is created, you can imagine that one would want to initialize the contract state in some manner. And this is really what is made possible by the constructor. So constructor is really a special function that gets triggered when a contract is created. A constructor is optional and there can be only one constructor for every contract. And these special functions are specified by using the constructor keyword. Some of the syntax and semantics has changed over the course of the Solidity versions, but this is how it has been in the most recent versions of Solidity. So constructors used to initialize the state of a contract when they are created and deployed on the blockchain. They're triggered when a contract is created and it's run only once. And once the constructor has finished executing, the final code of the contract is stored on the blockchain. And this deployed code does not include the constructor code that just finished executing or any of the internal functions that are called from within the constructor. And a constructor, from a security perspective, becomes very interesting because it really lets one examine what initializations are being done to the contract state, because if not, the default values of the specific types of state variables, for example, would be used in the context of the various contract functions. And this is an interesting and important aspect when it comes to evaluating the security of smart contracts. Another special function in the context of Solidity is the receive function. This is the function that gets triggered automatically whenever there is ether transfer made to this contract via send or transfer primitives in Solidity. Now we'll revisit these primitives in the context of security later on, but for now let's recognize that whenever a contract receives ether via these send transfer primitives, receive function is the function that gets triggered. And this function is also the one that is triggered when a transaction targets this contract but with empty call data. Recall that a transaction that targets a contract specifies which function needs to be called in that contract and what arguments need to be used within the data portion of the transaction. But if that data is empty, then the receive function is the function that gets automatically triggered in the contract. There can be only one receive function for every contract, and this function cannot have any arguments, it cannot return anything, and it must also have external visibility and a payable state mutability. Payable state mutability is something we haven't discussed so far, but what it specifies is that the function that has this payable specifier can receive ether as part of a transaction. And that applies to the receive function as well, because it is triggered when ether transfers happen, as we just discussed. The send and transfer primitives are designed in Solidity to transfer only 2300 gas. And the rationale behind this was to prevent the risk or mitigate the risk of what are known as reentrancy attacks, which we'll talk more in the security module. But this minimal amount of gas really does not allow a receive function to do anything much more than some basic logging using events. So from a security context, a receive function becomes interesting to evaluate because it affects the ether balance of a contract and any assumptions in the contract logic that depend on the contract's ether balance. Another special function in Solidity is the fallback function. This is very similar to the receive function we just talked about. There are some differences, however. This fallback function gets executed, triggered automatically on a call to the contract if none of the functions in the contract match the function signature specified in the transaction. This also gets triggered if there was no data supplied at all in the transaction and there is no receive ether function that we just talked about. Similar to the receive function, there can be only one fallback function for every contract. However, this fallback function can receive data and can also return data if required. The visibility is external, and if the fallback function is meant to receive ether, then it needs to use the payable specifier. Again, similar to the receive function, the fallback function cannot assume that more than 2300 gas can be supplied to it because this can be triggered via the send or transfer primitives in Solidity. And similar to the receive function, the security implications of the fallback functions have to consider that the ether balance can be changed via this function. So any assumptions in the contract logic specific to the ether balance need to be examined. Now let's switch gears a bit and talk about the types that are used in Solidity language. Solidity is what is known as a statically typed language, which means that the type of the variables used in the Solidity language within the contracts that are written in Solidity need to be specified in the code explicitly at compile time. And this applies to the state variables and also the local variables. This is in contrast to what are known as dynamically typed languages, where types are optional at compile time and are required only to be associated with the runtime values during execution. So statically typed languages perform what is known as compile time type checking according to the language rules. So when variables of different types are used, assigned to each other at compile time, the language can enforce that the types are used correctly across all these assignments and usages. Many of the programming languages that you may be familiar with, such as C, C++, Java, Rust, Go, Scala, are statically typed languages. So from a security perspective, the type checking really is a critical part and helps in improving the security of the contracts written in Solidity. Solidity has two categories of types. There are value types and reference types. Value types are called so because variables of value types are always passed by value, which means that whenever they're used as function arguments or in assignments of expressions, they're always copied from one location to the other. And in contrast, reference types are types that can be modified via multiple names, all of which point to or reference the same underlying variable. So from a security perspective, you can imagine that this becomes important because it really affects which state is being updated and what those transitions are in the states as affected by the transactions. Let's now take a look at value type. As we just discussed, value type is one of the two types in Solidity, where variables of these value types are passed by value, which means they're copied when used as function arguments or in assignments of expressions. There are different value types in Solidity: booleans, integers, fixed point numbers, address, contract, fixed size byte arrays, literals, enums, and functions themselves. So from a security perspective, value types can be thought of as being somewhat safer because a copy of that variable is made so that the original value of the original state itself is not modified accidentally. But then one should also check that any assumptions around the persistence of the values is being considered properly. So this will become clearer once we talk about the reference types and once we look at some of the security aspects in the later modules. But this is an interesting perspective that needs to be kept in mind when it comes to the types in Solidity. And in contrast to the value types, we have reference types in Solidity, which are passed by reference, which really means that there can be multiple names for the variable, all pointing to the same underlying variable state. There are three reference types in Solidity: arrays, structs, and mappings. We'll take a deeper look at each of the value types and reference types that we just talked about. But for now, again, from a security perspective, the reference types can perhaps be considered a little more riskier than value types because now you have multiple names, different names, all pointing to the same underlying variable. And this could, in some situations, lead to unintentional modification of the underlying state if the developer does not realize that this is really a reference variable and a different name that is being used for the same underlying variable. Let's now take a look at default values. Variables that are declared but not initialized have default values. And in the case of Solidity, the default values of variables are what is known as a zero state of that particular type. And what this means is that in the case of a Boolean, it has a value of 0 as a default. And this really represents a value of false for the Boolean. For unsigned integers or integer types, this is 0 as expected. For statically sized arrays and bytes 1 to bytes 32, each individual element will be initialized to the default value corresponding to its type. And for dynamically sized arrays, bytes and string, the default value is an empty array or string. For enum types, the default value is its first member. We haven't really looked at all these types, which we will examine in the forthcoming slides, but for now, it's sufficient to recognize that all these different types have a default value that is the 0 state for that type. And from a security perspective, this becomes important because variables that are declared and not initialized end up with these default values. And in some cases, such as an address type, the 0 address, which is a default value, has a special meaning in Ethereum, and that affects some of the security properties within the contract depending on how those address variables are used. Let's now talk about scoping, that is fundamental to every programming language. This really affects what is known as variable visibility, or in other words, where can variables be used in relation to where they're declared. And in the case of Solidity, it uses the widely used scoping rules of C99 standard. Take a look at this if you're interested. This is something that's widely used across many programming languages. So in the case of Solidity, variables are visible from the point right after the declaration until the end of the smallest curly bracket block that contains that declaration. But as an exception to this rule, variables declared in the initialization part of a for loop are only visible until the end of the for loop. This is again something that you'll be very familiar with if you're programmed in any of the high-level languages. Variables that are parameter-like, function parameters, modifier parameters, catch parameters, are visible inside the code block that follows the body of the function or modifier for a function modifier parameter and the catch block for a catch parameter. Variables and other items declared outside of a code block, such as functions, contracts, state variables, user-defined types, these are visible even before they're declared. This means that we can use or we can see the usage of state variables even before they are declared within the context of a contract. And this is really what allows functions to be called recursively. From a security perspective, understanding the scoping rules of Solidity becomes important when we are doing data flow analysis. And this could be in the context of a manual review where you're looking at the code yourself, or when you're writing tools to do static analysis on Solidity smart contracts.